Good morning, everyone. My name is Lei Xun, a final year PhD student. Today, I would like to give you an overview of my research in the past few years. I work with Professor Jeff Merrant, Jonathan Hare, and Bashir Al-Hashimi. All of our work are under the umbrella of Army ECS Research Center, as well as the International Center for Spatial Computational Learning. First, I would like to give you a high-level overview of what I'm doing. As shown in this figure, we can view a system as three abstract layers. At the bottom, we have a device layer. In my case, I'm working on embedded heterogeneous platform. At the top, we have application layer. Although I'm working on machine learning workload, but we do consider that multiple different workloads, including non-machine learning workload, are sharing the same hardware resources. In the middle, we have a runtime resource management layer. The runtime resource manager will monitor the hardware constraints such as temperature and power, as well as software performance requirements such as the latency, accuracy of the neural network. The runtime manager will try to meet these requirement constraints by tweaking the knobs in both software and hardware. There's a large body of work focusing on hardware side, such as the dynamic voltage and frequency scaling, task mapping, in which they basically trade off latency with power consumption. But in our case, we try to answer the question, can we do similar thing in the application layer as well? In another word, can we tweak some part of the neural network to do the trade-off between different performance matrices as well? By default, we cannot do that because neural networks are static by default, which means every time we want to execute a neural network, all the weights are used. Otherwise, we get a random result. Right? But there is an emerging field called dynamic neural network, which I will talk about now. As shown in this figure, we basically propose a specific training method to enable a network to be partially executed. We propose a method called incremental training and group convolution pruning. For a given static model backbone, we cut the convolution layers into groups and we combine them before the fully connected layer. And with such architecture, we then train groups, one groups at a time. For example, in step 1, we train group 1. After that, the model can make a prediction using the weight from group 1. And in step 2, we train group 2 while using the pre-trained weight from group 1. So that after this step, the model should be able to make a better prediction because we give it more capability, more parameters to use. And so on and so forth. We repeat this process until all the parts are trained. And after that, we have basically have a dynamic neural networks with 4 different configurations. The smallest model use 25% of the parameters, and the full model using all the parameters. They have different accuracy, latency, power, and energy trade-offs. But, well, basically, this is a software-only approach, but we need a system-level runtime management approach. Let me tell you why. So if I'm only aware about these dynamic neural networks, if I plot this energy versus latency trade-off on this figure, what we get is 4 trade-off points, right? For 4 different configurations. That is a very sparse trade-off space. On the other hand, if I'm a pure hardware person, I know nothing about dynamic neural networks. I can only tweak the voltage, frequency, task mapping, these hardware knobs. So what I get is 2 trade-off curves on this platform. One curve is for the ARM A15 big core CPU, another is for the ARM A7 little core CPU. A different point here representing different frequency levels. So we have more trade-off than pure software approach. But if we consider combine them together to do a hardware software to the system level approach, you can see that we have a much wider range of performance scaling. We can do the trade-off at a much finer grade. We also tested this on a different hardware platform. Now, let me tell you two more papers before we move to the next part. So this is a scalable neural network. It is state-of-the-art dynamic neural networks. It's using a specific training method called sandwich row. It trains the largest, the smallest, and some random model architecture between them during each training iteration, and they optimize the total loss of all the subnetworks to be minimum. And after this training, they can generate different subnetworks with different channel numbers. So this is also a channel scaling as to the previous incremental training method. And this is mutual net, which is very similar to Scalable, but with the additional input resolution scaling as well. All these methods, which basically we are making assumption that the model we are using are static, so we have to figure out how to turn them into a dynamic model. But as the field moving forward, or as the model design methodology moving forward, we start to see very different model architecture. And here's one. Here's the once-for neural network. The idea of OFA is that it trains a neural network once for a very, very long time. In this case, they also train the model for 6 months to generate 10 to the power of 19 subnetworks. The idea is that for different hardware platform, they can search a subnetwork from this OFA and deploy the model directly without retraining. But when I first saw this paper, I thought this is the perfect dynamic neural network I'm looking for. But I quickly realized it is not dynamic at all because the space is too large. The model search is very expensive and not feasible to do at runtime. So we think, well, if we cannot do it at runtime, we can do it at design time. But it turns out it uses a random search algorithm, which means that it might be okay if we want to find a model that is good enough for a given target, but it is not efficient if we found a library of models, as shown in the kind of the previous figure I showed, that a library of models with different trade-off points. If we use random search, it's very hard to get these trade-off curves here. But nevertheless, we think that we need a mental shift to design dynamic neural networks, because in the past, all the works are focusing on how we can propose specific training method to generate subnetworks. But as the model design methodology moving forward, as you can see here, the OFA probably have more subnetworks than we need. So instead of thinking about how to train, we need to think about basically how we can get the best model from OFA, and we combine them into new dynamic neural networks. Here we propose dynamic OFA, which use the OFA as the backbone model, and we do a lot of network search at the design time and take the most efficient, basically the Pareto front models, and combine them into a dynamic neural network. We still use random search here, but we're changing the search space to local search. Generally speaking, on the same platform, bigger models are more accurate but slower. So what we did is we searched for the basically most accurate, the bigger model first. Then we slowly switch the searching window by reduce the model search, by reduce the model size range, so that we can better find the model that are less accurate but fast. Basically the model on the Pareto front. We do the search for CPU and GPU separately because the based on previous research, they prefer very different model architecture. And this is also a benefit of using OFA as backbone, because OFA can provide a much flexible networks that can be efficient on many different platforms, different heterogeneous cores. Whereas the previous training algorithm can either do channel scaling or layer scaling, which they either are efficient for CPU or GPU, not both. So for heterogeneous, for SOC, we still need basically multiple dynamic neural networks if we use previous method. But if we use dynamic OFA, we just need one unified backbone with different masks for different heterogeneous cores. Here is a comparison between dynamic OFA with previous works. As you can see, compared to all the dynamic works, our work is much more efficient. We are still a little bit worse in terms of accuracy to the static OFA backbone, because these are individual models, 3 models with 3 set of weight, and we can do the fine-tuning to these individual models to increase the accuracy a little bit. But in our case, because we use one model that has many subnetworks sharing the weight, it's not easy to fine-tune them. But we do have the advantage of memory footprint, because we only needed to store one set of weight. And all the models for CPU, for GPU, and if we have other accelerators, they all sharing one backbone, one set of weight. They just need a different set of masks, different masks for different subnetworks. And again, as I mentioned before, previous dynamic neural networks train static models to generate subnetworks. They are all about how to train. But in our case, we see when the model design methodology moving forward, we need to start thinking about how we can utilize the benefit of OFA and how we can do the sampling. And in general, sampling is much quicker than doing training. Here I want to give you some case study. In here we run dynamic OFA with a second model to share one GPU resources. The x-axis is real time, the y-axis is the latency of dynamic OFA. As shown in the figure, in about 2.5 seconds, we deploy the second application, and you can see the green line, which is the latency of dynamic OFA, is suddenly become much slower because the second application uses a lot of GPU resources. So the runtime resource manager reacts to switch dynamic OFA to smaller configurations to temporarily trade off accuracy for latency. In another case, we have 2 dynamic OFA to share the GPU, so that basically they can give space to each other, so they don't have to switch to a much smaller model. They can just switch to a slightly smaller model, so they can coexist and meet their target. This is the end of my talk. You can feel free to ask any questions or chat me offline. You can contact me on LinkedIn, find all my publications on my Google Scholar, and find all my previous research talks on my YouTube channel, including a longer version of this talk, which was given at the Research Machine Learning Group and the Cambridge University Machine Learning System Group. Thank you.